Swayam Prabha. Digital India. Educated India.
E C2, help me, I sigma H, very good. Now, what we said is that we had already constructed gamma wave. There is no problem with that, I believe, right? Tell me what is gamma wave? I wanted the characters. 6204, great. And then from there we broke it down and we said gamma wave is equal to what? 3Ag plus AU plus 2BU. So 3 plus 1, 4 plus 2, 6. Alright? Now, next what we wanted to do is, we wanted to assign the internal motions, different kinds of internal motions of the molecule to these symmetry species. We want to know which is which. Okay? And the basis that we used for them are gamma NN, because NN stretch is unique, right? There is no reason why we should take it along with NF, the NFs, right? We can take it separately. Gamma NN is one. Second one was gamma NF, NF stretch, and the third one was the angles FNN or NNF, I don't remember what I wrote that time. Alright? Let us try to construct the reducible representations or irreducible representation, at least in one case, with this. Gamma NN. Let us talk about gamma NN first. What will be the character for E? 1. C2. C2 should be 1 or minus 1. There is a confusion, right? Because this is the normal mode. Now I don't have a nice model for the normal mode. That's the problem. Assuming you are colorblind, cannot differentiate between blue and black, this is the NN stretch, the whole thing. It does not matter if you turn it around by 180 degrees, it remains the same, isn't it? If this was a blue cap, this was also a blue cap. In that situation, even if I turn it by 180 degrees, does the sign change? If there is a question, please ask. Alekhya, question? Sure about this? This is 1. Please ask if you have a question. 1. Similarly, what about I? That will also be 1 because it is not a vector, it is just a line. Or maybe it is easier if I draw it like this, a double-headed line. Now, if you invert, if you perform C2, nothing changes, right? Arrows remain in the same direction. I think this is easier to understand. This is plus and this is minus. Okay, got it now? C2 or I will not take you from here to here. Very good. What about sigma H? Of course 1. Okay. So, where does this belong? Gamma NN would be equal to AG. One of the AGs is taken. So far so good. What about NF? How many NFs are there? 1, 2, right? So I can draw them like arrows, one arrow here, one arrow there, that is plus, right? And when they come in, they are minus, 2 arrows, right? 2 arrows separately. Okay. What will be the character of E? 2-dimensional basis. So character should be 2. Alright, Mehat? Or go? C2? What will be the character of C2? Why? Because these are the 2 arrows. This is one, this is one. Rolling arrows. Huh? These are the 2 arrows, right? So, and this is where C2 is. This is C2. If you perform C2, what will happen? The blue arrow will go where black arrow now is, black arrow will come where blue arrow now is. The interchange. So if you think of the matrix, what will the matrix be? 0, 1, 1, 0, off diagonal. The non-zero elements go off diagonal, right? So a rolling stone gathers no moss. That principle applies here also. Question, Orko? What about this? Okay. Are you okay so far? So it's going to be what? Minus 1 in C2? 0. What about I? The same thing will happen. Blue and black arrows will interchange places and they will go off diagonal. The ones will go off diagonal. So 0. And what about sigma h? 2. They are left where they are. So now you can break that down and you can tell me what is gamma NF. You know how to break this down? AI equal to 1 by h sum over I chi IR. Using that, you work it out, decompose it into constituent IRs and tell me what you get. Do we get AG plus AU or do we get AG plus BU? AG plus BU or AG plus BU? Or do we get AU plus BU? Or do we get 2 BU? AG plus BU? Do you all agree? Because I have forgotten and I am too lazy to work it out. So you have to tell me. AG plus BU is what you are saying. So I will go with that. You better be correct. Now it's a little better. Okay. AG plus BU. Now, what about F and N, the angles? This angle and this angle. What do you get? Character of E, character of C2, character of I, character of sigma h, 2. So once again, gamma NF NN is equal to AG plus BU, right? So this is the total. This is the total, and so far what have we got? I will call this gamma in plane. For all the in plane motions, I have got 3AG plus 2BU. So this AU is like poor Saurav Ganguly in the last season that he played for IPL. There is no taker, right? So what is this AU going to be? Of course, we have accounted for all in-plane motion that we could think of. Now you see, now we need to see the character table. How did you work all this out without character table? You have the character table with you. Very good. And today I brought this different book, partially because we are discussing this and partially because I don't have to zoom to show you the character table. The character table is printed in a little bigger font. You can read, can't you? Huh? So, C2H. In C2H, look at the characters of sigma H. Bg is -1, Au is -1. We don't have to worry about Bg because we don't have a Bg vibration anyway. We do have Au vibration, and character of that Au vibration, character of sigma H for the Au vibration is -1. That means 1, it has to be out of plane. No? Out of plane like this. If this is plus and yeah, this is plus and this is minus. So, plus to minus can be obtained by sigma H, isn't it? This is the molecule, right? Little more flexible fingers would have been very nice. One more joint, just one more joint in every finger would have done the trick. So, this is plus phase, right? And this is minus phase. So, this plus and minus, are they not related by sigma H? This is sigma H, plus, minus. Are they not related by sigma H? And how are they related by sigma H? The change sign, right? Plus becomes minus when you apply sigma H. Right or wrong? Okay, Mayak, got it? It's your question originally. So, if you now take this, okay, you work out all the characters. Think of this, this is plus, this is minus. What will be the character of E? 1. What will be the character of C2? C2? C2 is also 1, right? This is C2, 1, right? Then what is next? I? What will I be? I will be -1 and sigma H is -1. 1, 1, -1, -1, what is that? Au? Where did this thing go? What am I looking at? Oh, right. Au, 1, 1, -1, -1. Okay, but what I am saying is you don't even have to go that far because you already know that only Au is there, only one out of plane motion is there. So, just sigma H is good enough. But if you want, you can work out all the characters, no problem. Alright. See, the thing is, first of all, what we have done is we have just taken the in plane stretch and bend, right? From there we have got it. Let us see what the vibration should look like. But before that, let us complete this story. So, let me write this. Gamma out of plane then should be what? Au. Now, everything is taken care of. Now, let us think of individual types of motion. Where did we get Bu from? We got Bu from NF. Okay. So, what is NF? NF stretch. So, now for Bu the characters are 1, C2 gives you -1 and I also gives you -1. Okay. And we are talking about NF stretch. So, maybe we can think of something like this. One is going out and the other is coming in. Okay, this is plus, nice arrowheads. What will be minus then? Okay. So, now see, if I apply C2, what happens? Apply C2 to this. Do I not get this? right? So character is -1. Right? If I invert, what do I get? Do I not get this? Inversion means start from here, go to the center, go to equal distance on the other side. Now the beginning of the arrow has to show up there. That is inversion, isn't it? Start from this arrowhead, go to the center, go here, then arrowhead should come here. Start from this arrowhead, go to the center, go there, arrowhead should come there. So character of I is also -1, isn't it? So 1 -1 -1 1, what is that? That is BU. Shubhangi, question. Is a question, please ask. Okay. You are okay up to C2? What is the meaning of inversion? Inversion means you start from a point, you go to the center, right, and then go to an equal distance on the other side. Then you should get the same point. That is the meaning of inversion, right? So if I start from this point, start of an arrow, go to the center and come here. As a result of inversion, I should get a start of the arrow here. Let me draw on a fresh page. I'll now make it even easier for me to draw. Okay. So now if I invert this, what should I get? Start from here, go to the center, go here. Then I should get the start of an arrow, no circle. Start from here, go to the center, go here. I should get a circle. Start from here, go through the center, equal distance on the other side. I should get a circle here. And start from here to the center to here, no circle. Right? But then this is plus and this is minus. This is a plus phase of vibration, this is minus phase of vibration. So therefore, I get chi of H, chi of I to be equal to -1. All right. So what we have got is E C2 I sigma H. This character is +1, this character is -1, -1, and then here if you apply sigma H, what will happen? Circles will remain where they were, dots will remain where they are. So +1, 1 -1 -1 1. What is 1 minus -1 1? BU. Are you answered? Any other question? And don't forget, what we do is, for any kind of symmetry, we have to take a linear combination. If you have, say, some kind of a stretch and some kind of a bend, we always say, of the right symmetry, we say it is A1 stretch plus A2 bend. What determines A1 and A2? The bond strength, then atomic weight, etc. A lot of things. That is something that we cannot determine using symmetry alone. That becomes a computational chemistry problem. But then, even to start the computational chemistry problem, first of all, you need to determine the symmetry and you have to do a symmetry classification of the normal modes. Many of you have used Gaussian, I think. I can see two people who have used Gaussian, right? So there, if you look at the output of Gaussian, you will see that the first thing that is done, right, after geometry optimization is determination of the point group. Just go through the readout of Gaussian, you will see. Next, what they do is they perform a symmetry classification of normal mode, right? What? Right or wrong? Huh? What? You don't run Gaussian, you run Lorentzian or what? Okay. Point group is always C1. No, but then I have also run Gaussian, I have got the right point groups. I have not really used Gaussian so much. What I have used in the past is GAMES. GAMES is another program like Gaussian. The difference is like the difference between Windows and Linux. GAMES is an open source software, so you can change things. So anyway, so this is how it is done. First of all, you have to do a symmetry consideration, right? After that, you start your computation. Otherwise, computation becomes very complicated and you can lose your way. All right. Okay. Are we answered about the vibrations now? Now can I go ahead? Any other question on vibration, normal mode? No. I have to correct the mid-sem copies. Achha, lecture 16, slide 3. Now we go on to what we intend to discuss today. We intend to discuss today symmetry adapted linear combinations. Or what are called SALCs, sometimes they are pronounced as SALC. Okay, so you are going to talk about SALCs. Okay, now the real fun begins, to be honest. Right. See, I told you once, I think, not once, many times, that what we want to do in this course is that we want to play the astrologer. Right, we want to write down the kundali of molecules, right, and then we want to match kundalis. And now we are really in a stage where we have started matching kundalis. We want to we want to see what kind of symmetries different orbitals have, and then we see that which orbital can be a good bride for which other orbital. That is basically the idea of what we are going to do. Okay. Disclaimer is, I am not encouraging matching of kundalis in real life. It's just an example. So see, what we do is, now for the rest of the course we discuss bonding and a little bit of electronic spectroscopy. Now, everybody has studied bonding at some level or the other, right? So what is it that you do in bonding? What is it that you study? What are the different theories of bonding? VBT, MOT by and large, right? So you start with VBT. What are the advantages of VBT? Simple. That is the one answer. VBT is very simple, easy to conceptualize, easy to understand. What is the problem with VBT? The problem is it's too simple. When you don't write one word, two, then it is the advantage, and when you write that word, then it becomes a disadvantage, right? Many disadvantages, it's too simple. VBT can only work properly in the realm of two-centered two-electron bonds. Okay, anything beyond that is really beyond the scope of VBT. But then because of its simplicity, many times we try to make up stories like resonance. Resonance is just fiction. There is no such thing as resonance. Okay, so we just try to make up such stories in our attempt to expand the realm of this nice simple theory into more complicated situations that it is not really supposed to handle, right? It cannot handle anything beyond two-centered two-electron bond. So as long as we talk about the ground state, sometimes we even manage to get away with it, right? The entire organic chemistry teaching is based on pushing arrows and writing resonance structures after all, right? But you cannot really go beyond that, beyond a certain level if you want to work with VBT. That is why we want to use molecular orbital theory. Good thing about molecular orbital theory is that it is more general, right? It allows for delocalization, no issue. What is the problem with MOT? Don't forget we are in a symmetry class. So whatever I have said for VBT should more or less apply for MOT. I said that VBT is good because it's simple, bad because it's simple, right? MOT is good because it is general, it is bad because it is general. Because sometimes it overdoes things. Remember hydrogen molecule, everybody has studied MOT treatment of hydrogen molecule H2. So there it gives equal weightage to the ionic structure, which is obviously wrong. In VBT, the good thing is the coefficient is in your hand. You can say that the coefficient is 0.00000001. Okay? In MOT, in its attempt to be too general, it kind of gets over enthusiastic and unnecessarily emphasizes the ionic structure for H2. But there are too many advantages. One advantage is that it allows for delocalization without having to resort to any kind of friction. Second thing is that it gives you access to the excited states, right? And also it gives you the concept of antibonding orbitals. Very often we think that antibonding orbitals are useless, right? But they are not, they are extremely useful. Antibonding orbitals are used everywhere in things that are very well known to us, from things that we might not have thought about. Can you tell me about some examples of antibonding orbitals where they are useful in chemistry? There is actually a thin book called The Importance of Antibonding Orbitals by Orchin and Jaffe, very old book, it must be 1950s or 1960s. Okay, I don't know if it's there in the library. But can you tell me of any application of antibonding orbital that you know in chemistry? Reactions? In reaction mechanisms. Of course, then you must be an organic chemist who believes in MOT more than VBT, then only you can use it. Something more common? Catalysis? That is a part of reactions anyway. In structure of molecules. What I was, so once again you are giving me more difficult answers than what I am expecting. What I had in my mind was backbonding in case of carbonyl complexes. In carbonyl complexes, why are they so strong? Because the antibonding orbital is used to receive electrons from the metal, right? That is, I think, the most common example that everybody studies at a fairly early stage of their undergraduate study. That is one. The other example that I am going to tell you is something that you know but you have never thought about perhaps. So I am going to ask you the question that I really like to ask everywhere. Why is phenol acidic? Why is phenol acidic? Alcohol is not acidic. Why is phenol acidic? Benzyl alcohol. What is the formula of benzyl alcohol? pH? CH2H. And what is the formula of phenol? So you take away one CH2, it becomes highly acidic. If the CH2 is there, it is not acidic at all. Why? Once again, you have studied it, right? Everybody knows the answer to. Tell me. I see that I have scared people so much that they don't even want to give an easy answer. Why is phenol acidic? Come on, people. Conjugate base. What about conjugate base? It is stable. Why? So? See, now he guessed the answer, right? So, what we usually say, and I am okay with that, is that because this negative charge on oxygen is delocalized over the ring. Generally, we explain it by drawing those resonance structures, which are of course all fiction. But that is the right answer. The negative charge on O minus does get delocalized over the ring, right? But where will it go? I think you know this energetics of benzene, right? You know that there are 6 MOs, right? I am talking about pi MOs here. So these are the pi bonding MOs and these are the pi star anti-bonding MOs. Okay, and in this benzene ring, these bonding MOs are completely full. Okay, now see, if the electron cloud has to come in, where can you accommodate this incoming electron cloud? You can accommodate it only in the pi star orbital, right? And that is what is done. That is what makes phenol more acidic. Very good. That takes us directly to the next point that I am trying to make. which is actually which kind of forms the backbone of perhaps 50% of the research done in our group. It is an acid, fine. Does anybody remember what is the pKa of phenol? pKa of phenol or naphthol or some such thing, typically what it is? Yes. So 8 to 10 I will take an average, right? If you perform a pH titration curve, you get the inflection point at around 9.5 depending on which phenol you have taken. So it is acidic, but it is not all that strongly acidic. What is the meaning of pKa 9? That means the concentration of protons in the medium has to be as low as 10 to the power minus 9 molar for the molecule to be able to give up a proton, isn't it? So you need an alkaline medium. Now what I am telling you is this: suppose you perform a pi star excitation. Pi star excitation, everybody knows or not? Huh? Electron goes, some light of suitable wavelength is incident on the molecule, right? And an electron gets promoted from, let us say, HOMO to LUMO. So pi star excitation leads to the formation of what is called the pi star excited state. So this then will be the electron configuration. Oops. Let us say like this, 1 electron promotion. Now see what have I done? I have now created some space in the lower energy molecular orbital where the incoming electron cloud can be accommodated. Will that not be a happier situation? So what I am telling you is that an organic molecule which is acidic in ground state becomes a better acid in the excited state. This phenomenon goes by the name photoacidity. Right? Maybe you have studied this in a molecular photochemistry course. You people took that course last semester, right? Molecular photochemistry, organic chemistry. Was this discussed? Okay. So, but this is actually molecular photochemistry. Okay. So, what I like to say is that excited molecules do. See what happens when we are excited about something. We usually do it better. So, molecules similarly, when they are excited, they do whatever it is that they do in a little more efficient manner. And this is the reason. Similarly, you can show why an organic base, an aromatic base, should become a stronger base in the excited state. Okay. So this is called photoacidity. So if I can now construct the excited state pKa, if I can now calculate it, I can calculate it from something as simple as fluorescence spectrum. Okay. What should it happen? Should it be less than 9 or should it be more than 9? Less than, right? Less than 9. How much less than 9 do you think that we get? Say for beta naphthol, what does it become? Just take a guess. Huh? What? So it will be somewhere here, right? Something like this. This value for beta naphthol is 2. You are right. 2. Do you understand what has happened? This molecule in the ground state can give up a proton only when the external concentration of protons is as low as 10 to the power minus 9 molar. The same molecule, when you shine light on it, can give up a proton when the external concentration of protons is as high as 10 to the power minus 2 molar. We are talking about 7 orders of magnitude difference, no joke. That is how effective photoacidity can be. Alright, and things like that can only be accessed by molecular orbital theory, in case you forgot why this discussion started. So what we will do is we will mainly talk about molecular orbital theory for the rest of the course. We might talk about ligand field theory or crystal field theory when we talk about the inorganic complexes. 16, and the perils of copying is 5 became 4. Okay. So what we want to do is, we want to see how a discussion of symmetry, how a use of character tables can help us perform molecular orbital theory treatment on molecules. Organic molecules to start with, and then inorganic molecules.